We now know how to characterize our population of stars. We use their luminosity and we use their spectra to determine what type of star they are. We give their spectral type, that gives us their surface temperature, and we can now try to find correlations between luminosity and temperature and so on, and do population studies. What do the statistics tell us? Well, first of all, we notice that luminosity varies over huge ranges. We find stars with luminosities less than 1,000 times less than the sun, and stars with luminosities more than 100,000 times more than the sun. At the same time, the temperatures are ranging from 1,000 or so Kelvin, all the way to 50,000 Kelvin and more. And stellar radius, which we can compute if we know luminosity and temperature, varies considerably less. Now, how to organize the data was the subject of much speculation, and the successful presentation that we use to this day and that will accompany us for much of this class is in the form of something called the Hertzsprung-Russell diagram. This was invented by Hertzsprung and Russell in 1910. And here is a Hertzsprung-Russell diagram. It's a scatter plot of the stars. Each dot here represents a star. And in some sample, this is some part of the Hipparcos sample. And what do we have here? Well, the horizontal axis is temperature, with, by convention, temperature increasing to the left. So the hottest O-type stars are over here on the left. The temperature scale is at the top of the diagram. And the coolest M-type stars are here on the right. The vertical axis is luminosity. So we're plotting, if you will, luminosity against temperature. The most luminous stars with luminosities of over 100,000 solar luminosities are at the top. The dimmer stars are at the bottom. And notice that the luminosity scale is logarithmic, so that the sun is about in the center of this diagram, 1 solar luminosity over here, and above the next tag above it corresponds to 10 solar luminosities, similar distance above is 100 solar luminosities, and so on. And so what do we discern? Well, we certainly discern that stars are not distributed randomly in this plot. We have a pattern. Good. That's the beginning of understanding. Now we try to understand it. What is the pattern? Well, about 85% of all the stars lie along this one diagonal strip called the main sequence, because that's where all the stars are. And this runs from cool, dim stars over here in the lower right to hot, bright stars, or hot, very luminous stars in the upper left. And stars are scattered. Most of the stars are scattered in a very thin strip around this line called the main sequence. That means that if a star is a main sequence star and you know its temperature, you can predict its luminosity. Because we have this graph. We see a collection of stars scattered above the main sequence. What does it mean to be above the main sequence? That means that if you pick a temperature, by, in other words, a vertical line, these stars lie above the main sequence. They're more luminous than a main sequence star with the same temperature. How do you get more luminous maintaining the same temperature? That means their radius, their radiating area is bigger. These stars are bigger than main sequence stars. Suitably, they're called giants. We have this collected population of giants, and still higher above the main sequence are various supergiants and bright giants, and even larger stars, especially at the high temperatures. We see the very bright hypergiants and bright giants. And then there's below the main sequence, stars smaller than main sequence star don't seem to be there, except for this one arc towards the bottom. These are stars that, because they're way lower than the main sequence, are less luminous, even though their temperature is quite high. And so, suitably, they're called white dwarfs. These are very small, hot objects. We'll discuss where they come from later. But other than that, the plot is relatively empty. We've talked about the way that radius plays into this. We can compute radius, of course, given temperature and luminosity. Let's see how the radii of stars end up plotting on this diagram. This animation is designed to allow you to explore the HR diagram. Again, we have luminosity logarithmically on the left. We have temperature increasing from left to right. And you can sort of pick a luminosity and a temperature and move your little cursor along the main sequence. Note that changing the temperature at fixed luminosity is a horizontal motion. Changing the luminosity at fixed temperature is a vertical motion. And the red line gives us the main sequence. And what we see is that for the most part, stars on the main sequence have radii between 1 solar radius, this is where approximately the sun lies, and 10 solar radii, so temperatures of 100,000 luminosities, 100,000 times the luminosity of the sun, are achieved with a modest factor of 10 increase or less increase in radius. And the main sequence sort of follows a slow increase in radius with luminosity, except a little bit below the sun's radius, it suddenly dips below. The stars over here on the lower right of the main sequence are cool and smaller than you would get by just extending the main sequence. They go by the name red dwarfs. And we see that over here, where the giants were, are stars with radii of 100 and even 1,000 solar radii, way over here in the upper right-hand side of the plot. So this is a useful demonstration. We can plot here some of our nearest stars to us. We note that most of the nearest stars are, in fact, the sun-like or dimmer. On the other hand, if we plot the brightest stars, we see that most of the stars we actually see are going to be giants. This is clear. We can see giants farther out, where there is more of an opportunity for there to be more of them. And we'll come back. We'll be talking about HR diagrams a lot. For now, we have one more investigation to make. So what we saw is that if you know that if a star happens to be on the main sequence, all you need to do is measure its spectrum, and you can tell its luminosity, because being on the main sequence implies a relation between temperature and luminosity. But not all stars are on the main sequence. How do we tell? Is there a way, just by looking at a star, to tell if it's a hypergiant, a white dwarf, or a main sequence star? This was a very interesting question, and it was eventually understood in the 40s by Morgan, Keenan, and Kellerman that one could, in fact, by looking at the spectrum, distinguish, say, for a given temperature, looking at an F-type star, you know its temperature. What can you tell me about its size? And the result of their investigations was the following. Smaller stars at a given temperature tend to have denser, higher pressure atmospheres. It's in the atmosphere that we're observing the absorption line spectrum. A denser, higher pressure atmosphere exhibits broader spectral lines. As you condense matter more and more, the spectral lines broaden. Of course, if you condense it all the way to a solid, you get a black body spectrum. That's sort of the extreme case. And so you find that you can divide stars into sort of classes by their luminosity at a given temperature. And these classes range from 0 for hypergiants, way over here in the top, through type 1 for supergiants, type 2 for the bright giants, 3 are the giants, etc. 5, importantly, type V is luminosity class V is the main sequence, and down to luminosity class 7, where the white dwarfs lie way below the main sequence. In this language, we can now say that our sun, which had a temperature that made it a G2 star, somewhat in the middle of the type G temperature range, since it is a main sequence star, is a G2 5 star. So that's the spectral class, a combination of 3 designations, one for spectral type, one for the subtype within the type, and one for the luminosity class, gives you a 3-parameter, 2-dimensional position of a star. Roughly the first 2 letters tell you where it is horizontally along the HR diagram, and the last one tells you where it is in the vertical direction. You can locate a star based on that. So now that we know how to distinguish, just by looking at the spectrum, the position of a star on an HR diagram, we now have a great idea. Something called spectroscopic parallax. I warn you, it has nothing to do with parallax. What is spectroscopic parallax? It's a way of determining a star's distance just from looking at the spectrum. If a star is too far to make parallax measurements, can you still give me an estimate of its distance? The answer is yes. The reason is, if I look at the spectrum and I recognize the presence of a particular set of absorption lines, that gives me a spectral type. That gives me an estimate of the surface temperature. Moreover, if I can look at the breadth of those lines, I can figure out which luminosity class the star belongs to. Is it a main sequence star or is it a hypergiant? And once I do that, I can go back to my HR diagram and pick out the intersection of the corresponding curve with the corresponding vertical line for the temperature, and I can obtain a luminosity. So now I can read a star's luminosity with some accuracy right off of its spectrum. Now, if I know the luminosity, I can measure the brightness, and of course use our expression for luminosity, brightness, and distance to figure out the distance. So I can measure the distance to a star with some accuracy, even if it's too far for parallax. Note that this is another one of those ladders on the cosmic distance ladder. We know the calibration of the HR diagram because we've measured the actual luminosities of stars to which we knew the distance. Now we use that to extend. We can now measure distances to things that are too far for parallax measurements. That'll be very useful for us in the sequel when we need to know the distances to things that are too far for parallax. There are many other methods, all calibrated from parallax, but this is a good example of one, and I think we need a little more of a calculational example. Let's try to understand the star Alphakka. This is Alpha Coronae Borealis, and it's a whitish star. It's not the brightest star in the sky, but it's a bright one. In fact, we can measure its flux. A photometric measurement tells us that the brightness of Alphakka is 2.6 times 10 to the minus 12 times the solar luminosity. We look at its spectral lines, and we can measure its temperature. Its temperature is 9,700 Kelvin. It's a star of type A. It's hotter than the sun, A0 in fact, and Alphakka is a main sequence star as determined by the breadth of its spectral lines. So we go over to our HR diagram. We look at the main sequence. We look at the luminosity of an A0 type. This is the hottest of the type A stars, and we can estimate a luminosity of 74 solar luminosities. Alphakka is 74 times as luminous as the sun, and from this, if I want, I can figure out a distance because I have the brightness and the luminosity. I can also figure out Alphakka's radius. Remember, we had a relation between radii, luminosity, and temperature. This is the scaling relation, and I predict a radius of about 3 solar luminosities for Alphakka. Remember, we said that the main sequence goes from 1 solar radius at the sun all the way up to 10. Alphakka is part of the way up there. 3 solar radii is pretty reasonable. And we can, as I said, predict a distance to Alphakka based on using the luminosity and the brightness. Brightness is measured. Luminosity is predicted from HR. I plug in 74 solar luminosities here. I plug in 10 to the minus 12 or whatever for the Alphakka's brightness. And I find 5.5 million AU. I can convert that to parsecs with our 206,265 astronomical unit per parsec conversion. And I predict Alphakka's distance to be 25.7 parsecs. Now at that range, we do have parallax measurements. And so I can look up the Hipparcos database, read off the parallax angle of Alphakka. And of course, I remember that the distance in units of parsecs is just 1 arc second divided by the parallax angle. Plugging that in, I know that we have measured an actual distance to Alphakka of 22.9 parsecs. We have an error of on the order of 10%. This is typical of spectroscopic parallax estimates. There's some breadth to the main sequence, and we'll talk about where that breadth comes from. Stars are not exactly on a line, so the luminosity is not absolutely precisely determined by spectral class, but being able to measure distances just from looking at the spectrum of a star to within 10% is not bad.